Module 1, Lesson 8, equivalent ratios defined through the value of a ratio. And it gets a little picky, or it's a picky way of thinking of it. We're going to talk about the value, not a value of a ratio. And I'll try and make that clear as we go through. All right, learning targets, make comparisons with and within wholes. We are certainly going to be writing some ratios here. Identify and describe the fixed relationship between two values that are being compared, the unit rate. We're not so much looking at unit rate today. I can reason about comparisons and make predictions about what would happen if part of the comparison changes. We are going to be working on these first and third learning targets today. When we talk about the value of a ratio, it really comes into the equivalent ratios that are being talked about here in the third learning target. All right, I can show and explain that the value of a ratio A to B is the quotient of A divided by B. So to find the value of a ratio, it's a division problem. And we have to clarify that B cannot be 0 because, of course, we can't divide by B. I can explain that if the quotient of two different ratios, so for example, if I've got a ratio A to B and a ratio of C to D, if I do the division and get the same quotient, the ratios are equivalent. So we're actually looking and saying what happens when we divide. I can use the value of a ratio to solve problems. So I should almost put these in uppercase letters here, the value. And I can use the value of a ratio to decide if two ratios are equivalent. All right, exercise 1, look at the ratios below. If any of the ratios are equivalent, circle them with the same color. Now, so far, we have looked at doing equivalent ratios, and we've done a lot of tape diagram stuff. So what I'm going to do, and of course the other part of the equivalent ratios is the value of C, little c, that constant that we use. So I'm going to use a little tape diagramming and mix in a little bit of little c here to test these out. So I have a ratio of 1 to 2. Is there a value for c, my little c, my constant, that I could put into the boxes and get 5 to 10? Well, I know if I've got 1 and I multiply it times 5, I get 5. And if I multiply 2 times 5, do I get 10? And the answer is yes. So I know that 5 to 10 is equal to the ratio of 1 to 2. Now 6 to 16. I'm going to go back to my 1 to 2 here and check that. 1 multiplied times 6 would give me 6. 2 multiplied times 6 would give me 12. So I know that the ratio 1 to 2 is not equivalent to the ratio of 6 to 16. Now I could check the 6 to 16 to the 5 to 10, but why would I do that? I know that the 5 to 10 is equivalent to the 1 to 2. So there's no point in testing the 5 to 10 against the 6 to 16. I could step over here and take a look at the 6 to 16 and the 12 to 32. And that's a lot of tape diagramming. 1, 2, 3, 4, 5, and 16. Oof, gonna make a lot of little pieces here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, 16 pieces. The C value to go from 6 to 12 would be 2. And is 16 times 2 equal to 32? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yes, these two would be equivalent. And I have the tape diagram to prove it. Now, being equivalent means that they are going to have the same value. So let's take a look at this next part of exercise 1 here. We are going to find the value of the following ratios. And it says we're going to leave the answer as a fraction. We don't have to do the division. Yay! But we need to rewrite the fraction using the largest possible unit. Now, another way of saying this is that we need to write the fraction in simplest form. So we need to simplify it down. So the value of the ratio of 1 to 2. Well, let's take a look here at the ratio of 1 to 2. Is there anything I can do to get this to the largest possible units? Can I group any of these together to have a larger possible unit? And the answer is no. So the value of this ratio is 1 to 2. Now let's take a look at 5 to 10. Okay, here we have the ratio of 5 to 10. And the question is, can we put it into larger units? And that might be a little bit confusing, but the question is, can I group together the units I have? Remembering that each of these boxes represents a unit. Can I put these units together into some equal-sized groups? Well, I notice here that I've got 5, and I notice here that I've got 1, 2, 3, 4, 5, and I notice here I've got 1, 2, 3, 4, 5. So now I have grouped them together, and I have made groups of 5. So I'm now unitizing. I'm turning these 5s into groups. So here I have a group, and here I have a group, and here I have a group. And so this 5 to 10 here actually has a value of 1 to 2. I'm unitizing. I'm taking these little units and I'm saying, can I put them together in blocks or groups to make larger units? Largest possible unit. Now, another way to look at this would be to ask, is there a unit, a value for C, that I can divide both of these by? Well, I can take 5, and I could divide it by 5 and say that I'm going to make a single unit. And I could take 10 and divide it by 5 and say that I'm going to make 2 units. And that's exactly what the tape diagram I just drew looks like. We took the 5 and we grouped it together to make one group of 5, and we took the 10 and grouped it together to make 2 groups of 5. So another way to look at it. However, I really want us looking at the tape diagrams together. All right, so we have a ratio of 6 and 16. 1, 2, 3, 4, 5. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That should be 16 there. And I want to make some groups. Now, a little bit of number sense does make this a little bit easier. For example, I notice that both of these are even numbers. They're both multiples of 2. So I'm going to start out by making some groups of 2 and seeing how that goes. Group of 2, a group of 2, a group of 2, another group of 2, another group of 2, another group of 2, group of 2, a group of 2, a group of 2, a group of 2, and a group of 2. All right, well, that got me to 3 up here and 8 over here. So I'm going to jot down a note of 3 to 8. Now, the next thing I could say is, can I put together my groups of 2? Can I consolidate any further? For example, what if I made groups of 3? There's a group of 3 there. 1, 2, 3. Here's another group of 3. 1, 2, 3. Here's another group of 3. But I've only got 2 left over. So I can't group them any other ways without having leftovers. So this 3/8 here is the value of the ratio. Now, we've already established that 12 to 32 and 6 to 16 are equivalent ratios. We did that on the first slide. So the question is, can we prove that by doing this unitizing? And I know that this is a big tape diagram, but let's go ahead and give it a try. You know what? I'm going to make it even bigger. so that we can see what's happening. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And 32 is a huge tape diagram. 13, 14, 15, 16, 17, 18, 19, 20, 25, 27, 28. That's 29. 30, 31, 32. Okay. Now, I notice that 12 and 32 are both even numbers. So once again, I'm going to try and make some groupings of 2. 2 and 2 and 2 and 2 and 2 and 2. So it's important that you realize when I'm doing this unitizing here, when I'm building these units, that I have no leftovers. Everything gets to be paired up nicely. And here's 2 and 2 and 2 and 2. 2 more and 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 some more and some more and some more and some more and more and more and more. Okay. All right, so I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. But I notice the 6 and the 16 are still even. So I'm going to go back and I'm going to do some more unitizing. And I'm going to make some groups of 2. Now, it would have been smart if I had noticed that I could make groups of 4 to start with. All right, so now I've got 3 groups. And I've got 1, 2, 3, 4, 5, 6, 7, 8. Hey, the 6 to 16 and the 12 to 32 both are 3/8. So we've just used tape diagrams to prove that these two are equivalent and these two are equivalent. So the value of the equivalent ratios. Well, I couldn't help but notice that the values, when we got them written in the largest possible units, oops, that one wasn't half. That one was 3/8. When we went and got them written into the largest possible units, the values were the same. These first two had a value of 1/2. These second two had a value of 3/8. So here is a mathematical theorem, a statement. So if we have a ratio A to B, and B can't equal 0, and we have a ratio C to D, and D can't be 0, if they are equivalent, if my two ratios, A to B, is equivalent to C to D, then they have the same value, meaning their fraction forms will be equal to each other. So if two ratios are equivalent, their values are the same. They have the same value. Are there any examples you can think of that would prove this false? And these are called counterexamples. Is there anything you can think of, any example you can think of that would disprove this theorem, this idea? A theorem is a theory. Is there anything you can think of? I'll let you meditate on that. I'm not going to give you any hints or helps there. All right, so now we're going to use this to answer some questions. Tavon is training for a duathlon, which is a race consisting of running and cycling. Triathlon would also have swimming in it. The cycling leg is longer than the running leg of the race, so when Tavon trains, he rides his bike more than he runs. During training, Tavon runs 4 miles for every 14 miles he rides his bike. Now, the first thing we want to do is find the ratio. Well, I have a ratio of 4 to 14, and that is running to biking, to bicycling. So we have the ratio, and now we need to find the value. Now, in lesson 7, we worked on saying that the value is this 4 to 14. For every 4 miles he runs, he bicycles 14. The number of miles that he bicycles is 4/14. Sorry, the number of miles that he runs is 4/14 of the miles he rides. And if you need to, flip back in lesson 7 and see how we're writing those statements. So running is 4/14 of the bicycling. And now we need to find the value. We've got this in a value form, but it's not the value. We haven't got it written with the largest possible units. So at this point, you can bust out a tape diagram if you'd like. And we'll draw 4, 1, 2, 3, and 14. 6, 7, 8, 9, 10, 11, 12, 13. Okay. And I notice that these are even numbers, so I know I can make groups of 2. Now, last time I made the mistake of not checking if there was anything bigger than groups of 2. But I'm pretty sure the only number I can divide both of these by is 2, so I'm going to make groups of 2. So here's a 2, and 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 here's a 2. So that 4 is going to become 2 groups of 2, and the 14 is going to become 7 groups of 2. So here is the value. Simplifying it down and saying, okay, 2 7s. Now, I've shown this before in this lesson. I'm going to quickly show it again. So I've got this 4 to 14, and I can divide both of them by 2, making my groups of 2. That's what I do on the tape diagram. And 4 divided by 2 is 2, and 14 divided by 2 is 7. So I can find it using division. This is our little c, except instead of multiplying, like with 2 7s, we were multiplying both parts by 2 and getting 4/14. Now we're using the operation of division. And this is called scaling. Here we're scaling up because we're multiplying by whole numbers. And here we're scaling down because we're dividing by whole numbers. Now, another way that I could potentially look at this would be to involve prime factorization. 4 is equal to 2 times 2, and 14 is equal to 2 times 7. And now I can see that these 2's will divide out, and I will be left with 2 7s. All right, when Tavon completed all of his training for the duathlon, the ratio of total number of miles he ran to total number of miles he cycled was 80 to 280. And the question is that equal to the 4 to 14, or, more importantly, the 2 to 7 that we found in exercise 3A? Did he stick to his training regimen? Is 80 to 280 equal to the ratio of 2 to 7? That's the question. So what we need to do now is we need to take and get this and see if it's this. Now, we could draw a tape diagram, but that would be a huge tape diagram. I think it would be a little bit easier if we do some scaling down using some division. So I notice both of these are multiples of 10, 8 times 10, and 28 times 10. So I'll divide the 10s out, and that'll leave me with 8 over 28. And I notice that both of these can be divided by 4. So I've got 2 times 4, and I've got 7 times 4. So I can divide the 4's out, and I am left with a value of 2 7s. So yeah, Trayvon is sticking with his training schedule. This 80 to 280 is equal to 2 to 7, or the 4 to 14. All three of them are equal. 2 to 7 is equal to 4 to 14, which is equal to 80 to 280. Nice job, Trayvon. Nope, Tavon. Sticking with your training schedule. So in one training session, Tavon ran 4 miles and cycled 7 miles. Does this session represent an equivalent ratio? So we were looking at 4 to 14 in the first problem, which was equal to 2 to 7. And now we have a 4-to-7, and the question is Tavon sticking with his training schedule? Well, I don't think so, because I don't think that 2-to-7 is going to be the same as 4-to-7. I don't think there's anything I can do to make this 4-to-7 be equal to this 2-to-7. Looking at the tape diagram here, 2 and 7, 1, 2, 3, 4, 5, 6. I don't see how 4 and 7 are going to work. I can't do it. I can't do grouping over here to make this 2 and 7. It just isn't possible. So, no, he's not on his training schedule here in this particular day, and 4-to-7 is not equal to 2-to-7. All right, so how is the value of a ratio related to the ratio? Well, the value of the ratio A to B is the quotient of A divided by B. So the value is when we actually say, okay, here's what it's worth, and to find out what it's worth, we actually do some division. And so far, what we've done is written them as fractions. If two ratios are equivalent, then their values will be the same when they have a value, which all the ratios we're looking at right now do have a value associated with them. The value of the ratio is the quotient of the parts of the ratio. I'll say that one more time. The value, come back here. The value of this ratio is the quotient of the parts. The parts are A and B, and we find their quotient to find the value. When ratios have the same value, they are equivalent. All right, so taking a look at the learning target here, we wrote some ratios to represent some real-life situations. Got our first learning target happening here. And then we did a lot of reasoning about what makes ratios equivalent. And we expanded our thinking from using little c just for scaling up, just for multiplying up, to also using little c for scaling down, finding those largest possible units. All right, I can statements. I can explain and show that the value of a ratio A to B is the quotient of A divided by B, as long as B isn't 0. Because remember, we can't divide by 0. I can explain that if the quotient of two different ratios, A to B and C to D, is the same, the ratios are equivalent. Hopefully you can also use tape diagrams on simple ratios to prove this. I can use the value of a ratio to solve problems. We were doing that. We were asking if ratios were equivalent. And I can use the value of a ratio to decide if two ratios are equivalent. All right, that concludes Module 1, Lesson 8. If you've got questions, make sure you talk to your teacher. Go ahead and give your problem set a try.